Hello, everyone. Welcome to my talk on directing nanoplatelet emission with resonant Mie-like nanocylinders for luminescent solar concentrators. My name is Tom Veekend. I'm from the NWO Institute AMOF in Amsterdam in the Netherlands. And before I start, I would like to thank my collaborators at AMOF and my supervisor, Albert Polman, and then also the collaborators at Caltech and ETH Zurich. So what is actually a luminescent solar concentrator? Well, here you see a drawing that shows that a luminescent solar concentrator is based on a semi-transparent waveguide and can be used as building integrated photovoltaic module, for instance, here on the facade of a building. So it is based in blue here on this transparent waveguide, which can be glass or a plastic, with embedded emitters, luminophores, here depicted with the red circles. Then the idea is that solar light is absorbed by these emitters that will then emit inside the waveguide towards the side, where in green we have depicted the solar cells that will absorb this light that is total internally reflected within the waveguide to the sides where the light is converted. But besides this total internal reflection, there are also other mechanisms in this waveguide, such as scattering and parasitic absorption. And most importantly, the emission into the escape cone going from this glass to air, which is at about 42 degrees, where the light can be emitted, and then the probability of escaping out of this waveguide is very high. These escape cone losses amount to about 25% of the losses in such an LSC. And so this is a big loss mechanism that we will try to tackle. So in this figure from a recent paper together with the Caltech team, we have been using Monte Carlo simulations that track the absorption and emission in an LSC waveguide, where we have now introduced the anisotropic emission of the emitter as a parameter. Here in green is the probability of emitting in the total internal reflection angle versus the probability of emitting into the escape cone, where we can artificially change the ratio between these two, the fraction. And then we simulate the light emission through the LSC, in this case for a geometric gain of 20 and optical density of 3, which is a modest ratio between the top surface and where the geometric gain is a modest number for the ratio between the top surface and the size of the solar cell. And then we vary the POQY of the emitter, where at low POQY we have low LSC power efficiency, about 2%. And then as we increase it towards state-of-the-art POQY at like 99%, we increase the LSC power efficiency to about 5%. So that is relatively a big increase, but compared to the single junction limit, still quite low. But now in this simulation, we can also alter this total internal reflection angle probability, where in the isotropic case, emission into all angles is the same. We are at 75%, and we can now increase it artificially to 100%. And then at state-of-the-art POQY, we see this dramatic increase in the LSC power efficiency, where there are no photons lost anymore to do non-radiative decay. And also we don't lose them through the escape cone anymore, where really the compounding effect of these probabilities is shown for both absorption and again, reabsorption in the LSC. Now that we know of the importance of anisotropic emission, the rest of this talk is on how we try to achieve this. And our proposal is to use Mie-like resonances in nanocylinders, here made by Titania. And we optimize the shape of these cylinders by using FDTD simulations of dipole emission, where we average the three dipole orientations X, Y, and Z. Then by looking at different diameters and heights, we end up at these best performing values at an emission wavelength of 650 nanometers. And we get this average emission pattern that shows 93% of the emission outside of the escape cone, where the escape cone is here indicated by these red lines. So that is a big increase going from the 75% for the isotropic case. However, now we have a single emitter in a relatively big cylinder, and we will probably need more emitters as a function of the area. So going from the single emitter here, we now take a flat layer, where we could also imagine making the structure by having a triple layer of titania, quantum dot spin coating, and then again titania, where afterwards we use lithography. So doing these simulations, now we have to look at a little bit more cases where not only the emitter is on the center position, but also on several radial positions. And then we end up with a figure of merit of 85%, which is still a significant step from the 75% due to this compounding effect. Actually, the optimization does come back to the exact same shape of 500 nanometer and 150. Finally, we also should place not one of these cylinders, but several of them in an array. So here we do the simulation again for this square array, and we have simulations in FDTD for a single emitter on several 5 by 5 array to a 9 by 9 array. And then we end up with these hemispherical emission patterns that you see here on the right, where now the parameter of change is the pitch. So for a small pitch, here we see that the grating effects of this array actually emit within the escape cone, which is here indicated with a red circle. And then as we increase this pitch to 1400 nanometer, we see that we move out these grating effects to higher angles, lying outside of the red circle, and we regain our figure of merit to 90%. As 90% is higher than the 85% we saw before, because these simulations are still for a single emitter. And the only thing we wanted to check here is that the escape cone, that the emission is with outside of the escape cone. So we don't do all of the radial positions again. Good. Now we know that our design is final, and we can turn to fabrication, where we use e-beam lithography and reactive ion etching of this multi-layer of titania emitters and titania, where in our case, the emitter is a nanoplatelet that is made by the ETH Zurich team. And you can find details in this paper here below. I must say that we use lithography here for ease of control, but in the future for upscaling, it could also be made by soft conformal imprint lithography. And the final result after lithography and etching, we end up with this cylinder array of 100 by 100 micron on the flat glass substrate, which looks very well defined. And yeah, it's exactly as defined. And we have several of these patches for different array pitch. Then secondly, we can also look at the single particle resonance. For this, we use SEM imaging, and we do this on a sample that we fabricated on a silicon substrate, because otherwise the substrate would charge. So here you can identify the silicon substrate, then the first layer of titania, the nanoplatelet layer that has these features of the nanoplatelets, again a layer of titania, and finally the edge mask that was not taken off yet for this SEM image. We see a well-defined cylinder on substrate, and also relatively straight side walls, so exactly as we hope for. Good, we have nicely fabricated these cylinders, but then the question is, do the nanoplatelets still emit after all of these steps? And we can see here, yes, they do. We use an optical microscope and then look at the PL emission as a function of position over this red square box. And indeed, we see the emission coming from the multilayer, the flat multilayer of titania and nanoplatelets, and not from the bare substrate where we etched the layer away. And then secondly, we can also look at the emission from the cylinders, where we do the same photoluminescence mapping as a function of position, and we see that nicely these cylinders light up and not the areas in between. So there are no loose emitters. So now we know that the emitters still emit and they emit upwards, but in what direction do they truly emit? For this, we use Fourier microscopy. And the first thing we do is looking again at the flat reference. Here, the intensity of this Fourier image tells you in what direction the emission is emitted. So the center is straightly upward and going towards the side. This is under a steeper and steeper angle. And the 42-degree total internal reflection angle is this red circle that we identify by this Fourier image on a flat glass plate, indicating the escape cone angle, and that we can overlay with our final results for the two arrays. We have an array with the 800 nanometer pitch and 1400 nanometer pitch, and as we saw also in the simulations that you see here on the right for reference, on the 800 nanometer pitch, our emission is still within the escape cone. And if we make the pitch large enough, we actually move our diffraction angles out of the escape cone angle, and we have enhanced total internal reflection. In the experiment, you can observe that the grating orders are more oval than the square ones that we have in the simulations. This we attribute to the fact that the simulations are done for only this emitter in the center of the cylinder, and the experiment is of course for emitters on all positions within the cylinder. So this is great. We can actually fabricate and then also measure this anisotropic emission for LSCs. With that, I would like to conclude. We have seen in the beginning that escape cone losses are significant for LSCs, and how anisotropic emission can decrease these escape cone losses and dramatically improve the LSC efficiency as a result of that. Then we went on and designed and fabricated these nanocylinders that we use for directional emission with the embedded nanoplatelet, and how we use Fourier measurements to show where the directional emission goes and that it actually goes beyond the escape cone. With that, our results open up the way towards LSC devices with anisotropic emission. Thank you for your attention, and please ask any questions if you have them. Thank you.